welcome to Mickey Techie. Let's learn and let's teach. I would like to thank my family for continuous support and encouragement to do this kind of technical videos and I also thank my mentor Professor Surendran from Government College of Technology Coimbatore, and I would like to thank Almighty my God for making my health better for doing these kinds of videos. Today's topic of interest is thin cylinders and cell. Okay, what does mean by a thin cylinders and cell? What are all the examples? You can say if you are seeing a boiler or if you are seeing a cooker in our home, it is a thin cylindrical shell where the pressures are coming to picture. Due to the pressure and temperature, the materials will get stress and strain. So, uh, study of these things we are saying in thin cylinders and cells. Whereas there is cells are there, thick cylinders and cells are there. Their application were different. Today we are going to see thin cylinders and cells, how the thin cylinder and thick cylinders are differentiated by means of the T by D ratio, that is thickness to the diameter ratio, cell thickness to the cell diameter ratio. If T by D ratio is less than 1 by 20, then it is called as a thin cylinder. When T by D ratio is greater than or equal to 20, 1 by 20, it is called as a thin cylinders. We can say D diameter by thickness is greater than or equal to 20, it is called as a thin cylinder. When D by T is less than or equal to 20, it is called as a thin cylinders. Okay, now today we are going to discuss about thin cylindrical shells. Therefore, in thin cylindrical shells, there is a two types of stresses are acting. One is circumferential or hoop stress, and another one is a axial or longitudinal stress. And also, there is a maximum shear stress is producing due to the both circumferential and longitudinal stress. It will be discussed later. First, the circumferential or hoop stress is acting along the periphery of the thin cylinder or a shell. Therefore, sigma c is its notation. Sigma c means circumferential or hoop stress, that is equal to pd by 2t. Here p is the pressure induced in the cell and d is the diameter. We know that t is the thickness. And longitudinal stress, that is sigma L is equal to PD by 4T. From these two formulas, we come to know that the relation of longitudinal stress is equal to half that of circumferential stress. The longitudinal or axial stress is produced along the axis. Okay, it is along the axis. That is why the name is called as longitudinal or axial stress. Here, a very important thing is the thickness of the thin cylinder or a shell is designed based on the hoop or circumferential stress. According to the circumferential stress, how much circumferential stress is producing, according to that only the thickness is designed. Here, from these two formulas, sigma L is equal to sigma C divided by 2. Okay, that is our idea. And next one, the maximum shear stress in the thin cylinder, that is tau max is equal to PD by 8T. That is, it is derived from the formula of sigma 1 minus sigma 2 divided by 2. That is sigma C minus sigma L divided by 2. It will become PD by 8T. Next, it is an important formula, circumferential or hoop stress in terms of efficiency. If we know the boiler efficiency means the circumferential or hoop stress in terms of efficiency, sigma C is equal to PD by 2T into efficiency eta L. Here for the circumferential stress we have a longitudinal efficiency and for the longitudinal stress we have to put a circumferential efficiency. So likewise the formulas are given. Next one is the circumferential strain, circumferential or hoop strain. E1 is equal to PD by 4TE into 2 minus mu. Whereas longitudinal strain E2 is equal to PD by 4TE into 1 minus 2 mu. These two formulas are derived from the equation of the stresses in mutually perpendicular direction, strains in mutually perpendicular direction. E1 is equal to sigma 1 by E minus mu into sigma 2 by E. And also E2 is equal to sigma 2 by E minus mu into sigma 1 by E. Here mu is the Poisson ratio. Whenever there is a strain in both directions, we have to know the Poisson ratio. Poisson ratio come into picture. Next, if it is a volumetric strain, if it is a thin cylindrical shell, the volumetric strain EV is equal to 2 into E1 plus E2. We have a 2 circumferential strain plus 1 longitudinal strain. Therefore, the formula becomes PD by 4TE into 5 minus 4 mu. Here, a very important formula of the ratio of circumferential and longitudinal strains in terms of Poisson ratio. In terms of Poisson ratio, E1 by E2 is equal to 2 in 2 minus mu divided by 1 minus 2 mu. If we say the Poisson ratio in terms of M, E1 by E2 is equal to 2m minus 1 divided by m minus 2. Please take a note. The thin cylindrical shells are subjected to compressive load. Yes, the thin cylindrical shells are subjected to compressive load, and it is designed based on buckling strength. It is designed based on buckling strength. Okay, next one is an important thing. Cylindrical thin cell, spherical shell, thin spherical shell. For thin spherical shell, both longitudinal and both circumferential as well as longitudinal stresses are equal. Here, the shear stress is 0. The thin spherical shells are like as a ball, football. Football we know, football, volleyball. That is called as a thin spherical shell. That kind of boilers, where we have a spherical boilers also. The spherical boilers are having zero shear stress, whereas a circumferential and longitudinal stresses are PD by 40. Here the volumetric strain becomes EV is equal to 3 into E1. We know that the hoop strain or longitudinal strain E1 is equal to E2 is equal to PD by 4TE into 1 minus mu. Here EV is equal to 3 times of V1, therefore 3 into PD by 4TE into 1 minus mu. So that is all, my friends. I hope you have enjoyed my video, and please like, share and subscribe this technical content for the better understanding. If you have any doubts, please let me know in the comment section, and I will explain and I will make a video for your betterment. Thank you.